Today we are going to switch back to comparison based sorting algorithm. We have seen many of those, and today we'll see the last of them, which is quite important in algorithms, and that is quick sort. So yeah, quick sort is a kind of splitting algorithm like merge sort only. So like in merge sort you split your array into two equal halves. In quick sort also you split your array into two halves. Now there is big difference. In merge sort I said two equal halves, but here I am just saying two halves, and these two halves need not be equal in quick sort. This is the most important distinction between quick sort and merge sort, and we'll understand that. I mean, I've just said the most important thing in your mind, and now you will see it on your own automatically. So it works on this philosophy that, let's say there are following elements in an array: A0, A1, A2, A3, A4 and A5. Let's say these elements are there. Okay, then what it tries to do is it tries to split this array into two parts, and in order to do that, what it basically does is it picks any random element. I mean, that random element can be first element, that random element can be last element, it can literally be anything. So for sake of convenience, right now I am picking the first element. Okay, I repeat again, you can pick any random element, it's totally up to you, but for sake of convenience I am picking first element to be that random element. Okay, now what it does is it places this random element at its deserving location in the array. At its deserving location in the array. So what I mean by that is, let's say I have elements like 15, 22, 1, 7, 9, 24. Okay, let's say these are the elements out there. Can you tell me what will be the deserving position of 15? In the sorted array, what will be the deserving position of 15? Can you tell me that index? So if this becomes sorted, then I will get 1, 7, 9, 15, 22 and 24. So the deserving position of this is 4th position. Okay, so I want to basically put it at 4th position, and that 4th position is index 3 basically, right? Cool. So the point is that I do not want to sort the entire array, because if I try to sort the entire array, then maybe I'll have to use some other algorithm for doing that, and I don't want to use that. Rather, what I want to do, I want to position the randomly picked element. So I want to position the randomly picked element at its deserving place. Deserving place in sorted array. So now the question in front of me is that how to decide that what will be the deserving location of the first element, which is randomly picked element. Can you think of a very simple way to do that? Anyone? Order n. We can do it in order n, right? So what would be the approach? Compare and insert doesn't make sense. My question is simple. Tell me the position where it would lie. Okay. Count the number of smaller elements. Yeah, as simple as that. So what I can do is, let's say this is my randomly picked element. Now out of everything from here to here, I'll count the number of smaller than elements or smaller than equal to elements. That how many elements over here are smaller than or equal to me. So let's say you pick 15, and can you tell me how many elements from here to here are smaller than equal to 15? How many elements? There are 3 such elements, and those 3 such elements are 1, 7 and 9. Okay, so it's definite that 1, 7 and 9 will come before this 15 in the eventually sorted array, right? So what you can do is, once you have figured that count out, okay, then you can very easily say that 15 will come after 3 elements. So since it is coming after 3 elements, its index position will be index 3, okay, because indexing begins from 0, and I mean you can just sort that out on your own. So what would you want to do? Can I say that if, let's say, this was my array, and okay, to figure out that the count of elements smaller than equals to 15 is 3, how much time would have taken? In how much time you can count those? You can count that by running a single for loop, right, in order n time. And after figuring that out, the only job that you are required to do is to position it over here, which is over here. So can you tell me, how do you position this over here? How do you position this over there? Because if you position it over there, you'd want to swap, right? You'd want to swap 7 with 15. So cool. So you would want to swap this 7 with 15. And if you do that, 7 comes here and you have 22, 1, 15, 9 and 24. So see, 15 has come at its deserving location, right? Now, my question from you is, 15 has come at its deserving location. So this slot is happy, right? Now, can you recursively make the same function call for left portion and right portion? Can I do that? Can I make the recursive function call to do the same thing that I did in the original array to be done in the left half and to be done in the right half also? Can I do that? Yes, no. I can do that, right? I can do that. So let's take a look just at the left half. In the left half, what will be your randomly picked element? Let's say you are sticking to the convention of always picking first element as random element. So it will be 7, right? So now you would try to locate 7 at its deserving position. Okay. So where will you locate it? Can you tell me which element will 7 get swapped with? 22, right? Okay. Once you do that, so what happens? 7 comes here, okay, and 22 comes here, and 1 comes here, and 15 was here anyways. So 15 and 7 have been fixed. Okay, I'll come to this part later. Now this portion is just of size 1. So what will you do? This subarray is just of size 1. So what would you do? Would you simply terminate? Would you terminate? If you are trying to sort an array whose size is 1, would you terminate or not? You would terminate, right? So you would terminate, and termination means that 22 would be here, 1 would be here. Now you would do the same thing over here. Tell me one thing, whatever you have got till this point, is it sorted? No, it is not sorted. Can somebody tell me why it is not sorted? Because I blindly did what I said. I simply said that I need to position an element at its deserving position, and by positioning you told me swapping, and when I swap I get 2 halves, okay, left half and right half, and then I do the same thing in left part and right part, correct? So why does it not work? Take a look and tell me if that makes sense to you. Yeah, that makes sense, right? So it's not enough to just position this at its deserving location, but apart from positioning this 15 at its deserving location, you would want that all the elements that are smaller than equals to 15 come here, and all the elements that are greater than 15 come here, because this recursive problem will be different from this recursive problem. Okay, so it would never happen that you would never be able to throw this 22 towards the right of 15. You would never be able to throw this 9 towards the left of 15. So you have to ensure this thing. So this is second most important thing about quicksort. Okay, that you do not just position your randomly picked element. This randomly picked element, this is also called as pivot. So you do not just position pivot at its deserving location, but you also ensure that everything that is smaller than equals to pivot comes to left, and everything that is greater than pivot comes to right. Okay, now here you have to be very careful from coding perspective. You can either stick to the rule of putting all the elements that are smaller than equals to 15 here and greater than 15 here, or you could have positioned everything that is smaller than 15 in the left and greater than equals to 15 in the right. Would it make any difference, guys? From functional point of view, in the sorted array, Would it make any difference? It would not make any difference, right? You can, guys, is that clear or not? The elements which are equal to pivot, they can lie in its right side also and left side also, right? So it's up to your implementation, how you want to implement it. I ask again. So now basically what I would want is that when I position 15 here in this array, then all the elements that are smaller than equals to 15, and which elements are smaller than equals to 15, those are 179. So those 179 must come over here. Now they can come in any order, they can come in any permutation, they can come in 971, 917, whatsoever it is, and everything that is greater than 15 should come to the right. So 24, 22 or 22, 24, whatsoever it is. They can come in any permutation. The only thing is that everything smaller should be in the left and everything larger should be in the right. This is the only constraint. Okay. Yeah. Now what you can do is whatever you did over here in the actual array, that you can perform in this subproblem, and that you can perform in this subproblem also. Okay. So this is how your job would get done. So my first question to you is simple. Can you convert this array into something like this, where your pivot has reached its deserving position and also everything smaller is in the left and also everything larger is in the right? Can you think of an easy way to do this? Again, extremely trivial. What I asked is extremely trivial. Yeah, extra space, very good. So that is the way you give intuitive responses. Okay, so how many of you understand that if I utilize some extra space, my job will be done? It will be done. It will be very easily done. Okay, so what you can do is, let's say this was your array. So you can have two arrays with you, lesser and bigger. Okay, so in lesser array, while you are traversing from here to here, in the lesser array you will put all the elements which are lesser than or equal to 15. So this will contain in it 1, 7 and 9. And in the bigger array you will put everything that is greater than or equal to 15. Okay, sorry, greater than 15. Okay, so hold on, this was to store everything smaller than equals to 15, which is smaller than equals to pivot. So 15 will also come here, right? In this bigger one you will get everything that is strictly greater than 15. So what you will get is 22 and 24. And once you have created this array and created this array, then you just need to do what? You just need to copy this over here and then later copy this after that. Okay, so this way you can very well ensure. Okay, if I have to be specific about order, while you iterate, first you will see 15 and you will put 15 over here. Okay, and then 1 and then 7 and then 9. But the point is that 15 was your pivot, so you can handle 15 in a different way. What I mean by that is you will put 15 over here, okay, which is at its deserving location, which you anyways know for sure, and then for all the other elements, okay, that are not this, that were not at this index, they can be positioned here, and all the greater elements can be positioned over here. And now let's say this deserving position of pivot was position k, okay, and this was I and this was j. So your original problem was spanning from I to j, and now you figured out k, where you positioned your pivot. So can you tell me what will be your what will be the indices for your left problem and right problem? What will be the indices that would determine your left subarray and right subarray? Guys, you have put 15 at its location, which was k, this was I, this was j. So how do you determine this and how do you determine this? Can somebody tell me now? The left one would be spanning from I to k minus 1, and the right one would be spanning from, what is this? K minus 1. And what is this? K plus 1. So the left one would be from I to k minus 1, and the right one will be from k plus 1 to j. Now refer to the point that I said before. Is it necessary that both these halves will be of equal sizes? Is it necessary? No, it is not at all necessary. It depends upon k. And what is k? K is where you have positioned your pivot. So at times it can happen that the left subarray is very big and the right one is very small. So equal division is not being guaranteed. Okay. Okay, let's take another example. What if you had an array that was already sorted 1, 2, 3, 4, 5. What will happen over here? What will happen over here? Your pivot will be 1. So will you swap 1 with anything? If yes, what will you swap 1 with? You will swap 1 with 1 only, right? Correct? And that would mean that this will just have a right problem and this will not have a left problem. Right? So this will just have a right problem which will be invoked for 2, 3, 4 and 5. Correct? How much time is spent here? How much time is spent here in putting 1 at where it is and then doing those entire steps? Order 1 very bad. Order n. I spoke about it before only, right? That you do partition every time. See, whatever you have done over here, I did not want to name this, but this thing, whatever you have done, this is called as partition. How did you say order 1? How did you determine that 1 has to be placed over here? You have to perform that partition, right? You have to put all the elements that are lesser than equals to pivot in one array and then the other array, and then you have to do your job, right? So everywhere, at every level, you are doing a partition which is order of n, around order of n, right? Now the size of this is n minus 1. Okay, so again, what will happen? Will this 2 go anywhere? No, this 2 will remain wherever it is. So there will be no left problem, there will just be right problem, and that right problem will contain 3, 4, 5 in it. Time spent over here is order of n minus 1. Now again it will divide, there will be no left problem, just right problem with 4 and 5 in it. Time spent over here, order n minus 2. Can you visualize this tree, guys? How many of you can visualize this tree? How is it working? Right? Can you tell me the depth of this tree? How deep will this go? N. Because the size of the problem is being decremented by how much unit? In each step, by how much unit is the size of problem getting decremented? By just 1 unit. So from n it will become n minus 1, then n minus 2, then n minus 3, then n minus 4, so on till eventually it will become 1, wherein it will terminate. And what will be the time complexity of this? So at the first level order n, second level order n minus 1, order n minus 2, last level order 1. So from 1 to n it will be order of n into n minus 1 by 2, which is nothing but order of n squared. So this is the worst case for quick sort, where the divisions that are happening are extremely biased. So one portion does not exist and the other portion exists and is very large. For which kind of arrays this kind of scenario would happen? Can somebody tell me that? For which kind of arrays would this scenario happen, which is already sorted? Sorted in which order? Ascending or descending? Okay, if it is sorted in descending, then it would not happen. What do you think? If it is sorted in descending, see, you want to sort the array in ascending, right? Now the given array, if it is sorted in descending order, would this problem happen or not? It would happen, right? It would happen. The only change would be that there will be left problem and there will not be any right problem. So if you take an example, let's say I have got something like 5, 4, 3, 2 and 1. Okay, so where will you locate this 5? Where will you locate this 5? With what element this 5 will be swapped? You will swap it with 1, right? So what would happen, that this 5 would come over here, okay, and this 4, 3, 2, 1 would have come over here. So there will not be any right problem but just left problem. And now again the same thing that happened over here, this 4 comes over here and you have got 3, 2, 1 over here. So order n time here, order n minus 1 time here, order n minus 2 time here. So quick sort is one such algorithm where if the array is highly sorted or highly unsorted, then it will take the worst case complexity, and that worst case complexity would be order n square. What was the worst case of merge sort? It was always n log n. Merge sort was always n log n, because without any discrimination, it always bifurcates the array into two parts. And the major philosophy over there is merge procedure, right? So that was order n log n, but this thing can be order n square in the worst case. Okay, cool. And this is the, so yeah, the heart of merge sort was merge process, but the heart of quick sort is what? Can somebody tell me? Partition process. Partition process, which partitions array into two groups and calls them. So in the merge sort, if I take a look at merge sort, the recurrence relation was something like this. So there was a problem of size n. It was breaking it into two problems of size n by 2, and when those two problems were solved, it was performing a merge which used to take order n time if both the subarrays are of size n by 2 and n by 2. Okay, but here, so this is recurrence equation for merge sort. Would the quick sort also have such kind of recurrence equation, or would it have something different? What do you say? So you say it will have different. So let's say you position your element, let's say A0, A1, A2, A3, A4 at a place such that the size of this is k. Then can you tell me roughly what will be the size of this? If the first portion, which is the left half, is of size k, then what will be the size of right half? It will be roughly n minus k minus 1. Yes, n minus k minus 1. So this problem will be pk, and the right problem will be p of n minus k minus 1. And how much time does the partition take at any level? So it will take order n time if the original problem was of n. So this is the recurrence equation for quick sort. Okay, in case of sorted array, what used to happen, that this thing was t1 and this thing was always n minus 1, roughly n minus 1. So when the array was completely sorted or completely unsorted, then this equation turned out to be tn equals to tn minus 1 plus order of n, right? It turned out to be something like that. And if you expand that equation further, you will see order n square coming up as the value of tn. Can you see that? How many of you see that? If you expand that equation, will you get order n square? Yes, you will get, because tn minus 1 can be written as tn minus 2 plus order n minus 1. So now you have tn minus 2 plus order n minus 1 plus order n. So eventually you will get that. Okay, but if let's say the elements of the array are in such a way, see, the input array elements are in such a way that every time you are able to group them into two equal halves. Okay, every time you are able to group them into two equal halves, then how will this recurrence equation look like? Will it start looking just like merge sort then? Right? Then it will start looking like merge sort, right? So the best case time complexity of quick sort is n log n. And this will only happen when you have got such a kind of input where every time when you are partitioning, you are getting the two problems of equal sizes. So the best case time complexity is n log n and worst case time complexity is n square. So the time complexity of quick sort fluctuates from n log n to n square. Okay, cool. What is the extra space over here? Any extra space requirement? Order n. So order n is the extra space requirement when you are using an additional array to store the lesser than equal to elements and additional array to store the greater than elements, right? So that way I can say that partition over here is utilizing some extra space. Okay, and also there is some extra space for recursion stack. Okay, what can be the largest size of recursion stack? Can somebody tell me? Order n, when you are getting this skewed kind of thing for sorted or completely unsorted array. And in the best case, it can be order log n, just like merge sort, correct? Cool. So now I have to think of a partition process which use order 1 space. So it is still able to function in order n time, but it does not require any extra space. Okay, so anyone who has some idea where I can do this thing in order 1 space? And now this is very important thing what we are going to learn, that version of partition which takes constant space. Anyone who has learned this before, or you know something about it? So I will give you a quick example of something. So let us just take a sample array. So let's say your array is 4, 2, 1, 3, 6, 5 and 7. So tell me one thing, just like in merge sort, what you do, whenever you make a merge sort function call, how do you pass your array or subarray? You pass the starting index and ending index, right? That is what you do. So here also you would need to pass your starting index and ending index. So initially you would be talking about the entire array, and the starting index is 0 and ending index is 6. Okay, cool. Now you would imagine this thing as your pivot, 4 as your pivot. Can you tell me at which index 4 will go? It will go at index 3, right? So what you would do is, first step which would be of partition, that partition would put 4 at index I equals to 3, and then everything that is smaller than or equals to 4, which are 2, 1 and 3, those would be pushed to the left of 4, and those would be part of the left recursive problem. And everything greater than 4, which are 6, 5 and 7, will now be the part of right recursive problem. So basically what would happen is that now you would end up calling 2, 1, 3, which got pushed towards the left of 4, which will be from index 0 to I minus 1, from index 0 to 2. So this is your left problem. And your right problem, can you tell me right problem? So in the right problem, you will have 6, 5, 7, which have got pushed to the right side of 4. Okay, right side of 4 means from I plus 1 till 6. So it will be from 4 till 6. So did equal division happen over here? Yes, no? So here equal division happened, right? Because my pivot was such and the array was basically such that the left problem and right problem ended up having same size. Okay, now whatever you did here, that you would do here also, right? So now again here your pivot is 2. Can you tell me out of indices 0, 1 and 2, at which index this 2 will come? At which index this 2 will come? Yeah, so you will put this 2 at index equals to 1. So when this 2 comes at index 1, now everything smaller than 2, which is 1, will come to the left. Okay, so now you will have 1, and this 1 will reside in the, so the portion of this will be from 0 to I minus 1, which are from 0 to 0. Similarly, your right problem, it will just have 3 in it. Okay, and this resides towards the right side of I equals to 1, so that will be from I plus 1, which is 2 to 2. Will you mark this and this as your termination conditions? Right? Yeah, you will mark these and these as your termination conditions. And now again here, what will you do? You will just pick 6 as your pivot. Where should 6 go? At which index will 6 go out of 4, 5 and 6? 1 is not right. Is 1 even an index in that range from 4 to 6? No. 6 will go at 5. Okay, so you will position 6 at index 5, and then what would happen is that everything smaller than 6, which is 5, will come in the left area, which will be from index 4 to I minus 1, which is 4. And similarly in the right side you'll just have 7 from index 6 to 6. This is termination, this is also termination. So what actually happened? You can see very clearly that 1 remained at index 0. At index 1, 2 came. At index 2, 3 came. At next index, 4 came. At next index, which is this, 5 came. Then at next index 6 came, and then 7. So see, I gave you example of such an array where it was possible to, see merge sort kind of thing, where every array is being divided into two equal arrays, but it is not necessary. Okay. Now come to an important part. Okay. And that part is, how can I do this thing? So every time I am doing this partition thing, time taken is basically order of the length of the subarray, and the extra space that I require is also order of length of subarray. Okay, so instead of creating new array every time, you can have a global array, lesser and bigger, which can be of size n, and you can reuse it at every recursion level the way you are using auxiliary array for merge sort. But now I am interested in such a kind of partition which uses order 1 extra space. Okay, so let's focus our attention over there. So constant space partition is what we are going to understand. Okay, so just think of it in this way. Let me take any random array. Let me take this only, for example, or a new array for simplicity's sake, 4 1 2 6 3 5 7. So first thing that you should keep in your mind is, do not mug this concept that always my pivot element will be first element. Your interviewer at times can consider middle element also as pivot. He can consider last element also as pivot. Okay, but if your concepts are clear, you should be able to deal with all of those. Can somebody tell me how can you deal with those? If let's say your interviewer says that, hey, instead of considering first element as pivot, you consider this element or this element or this element as pivot, how can you work your way out? So considering anything as pivot means what? That thing should be positioned at its deserving location after the end of partition, right? So if somebody tells you that, hey, instead of using the first element, you use third element as pivot, what I will do is, I will simply first swap this with this, and then I'll apply my regular algorithm where 2 will be positioned at its deserving position. Okay, if somebody asks you to pick last element as your pivot, that also you can do. You can just swap this last element with the first element. After swapping, then you can apply your regular algorithm. Okay, so see, picking a random pivot is not something that I should worry about, because that is just a matter of swap, which is just a common sense and nothing else. But most important thing is that how do I partition it without using any extra space? Okay, without using any extra space. So let us try to understand that. So I am reconsidering this array 4 1 2 and this thing. Okay, so let's say I consider first element as my pivot. Okay, now what I can do is that I am concerned about these elements, right? That these elements somehow get organized in a way that all the elements which are smaller than equals to 4 are in the left of 4, and all the elements that are strictly greater than 4 are in the right side of 4. Okay, so how to do that? So let's say I have a pointer over here. Okay, pointer is just a variable. So if this was, let's say, if this was low and this was high, then my L is equals to low plus 1. Okay, and I'll have another pointer h over here, so this h will be equal to high. So I'm interested in the portion from low plus 1 till high. Okay, and for that I am using L pointer and h pointer. Okay, now tell me one thing. If you want everything smaller than equals to 4 to come to left and everything greater than 4 to come to right, as long as you are getting such kind of elements which are smaller than or equals to 4, would you want to do anything? Is it a good idea to push them to right side? Is it a good idea to do that? No, it is not a good idea. If you are getting the elements which are smaller than equals to pivot, why to push them to right? It doesn't make sense. You want right side to contain the elements that are strictly greater than pivot. Okay. So what will happen when you see that this thing obeys this rule, you will move ahead. again you see that this thing obeys this rule, you will move ahead. Does this element obey this rule? No, it will not obey this rule. So you will stop there. You will just stop there. Okay. Now, the way you incremented your low pointer, how you incremented, as long as you were getting something like this, that your A of L, as long as this happened to be smaller than equals to A of low, you kept on doing L plus plus. Isn't it? Yes, no. This is what you did, right? Now, the same thing can you do from left side? From this side? Can you do it? Yes, no? What will you do? Here, instead of incrementing the pointer, you will decrement the pointer. And when will you decrement the pointer? Tell me. When will you decrement the pointer? When you are getting which kind of elements? Which are greater than 4, right? So as long as you keep getting elements which are strictly greater than 4, you will keep on decrementing this. So this H will come here. Now again, this is also greater than 4. So now this H will come here. Okay. Okay, now what would you want to do? At this point of time, when this is 6 and this is 3, what would you want to do? Would you want to swap them? Yes, no? Yes, you would want to swap them. Swapping is a good idea. So now you would just want to swap them. So if you swap them, 3 comes here and 6 comes here. Okay. Now again, that rule again starts, where as long as you are getting elements that are smaller than equals to 4, you move it. So now it will come here and it will just stop here, because now 6 doesn't follow this rule. Similarly, that backward logic will also come into play, and as long as the element is strictly greater than 4, it will change and now it will stop here. So at this point of time, whenever you see that L has become greater than H, you would want to break, right? Okay, so at the end of the day, what happened, if you take a look, at the end of the day, L would have reached at that element which is strictly greater than 4, and everything towards the left of L would definitely have been smaller than equals to 4. Similarly, H would have stopped at that element which had been smaller than equals to 4, and everything in the right side of H would have definitely been greater than 4. So this kind of thing has happened, that 1, 2, 3 came over here and 6, 5, 7 came over here. Okay, but the game is not over till now, because now I want 4 to come to its deserving location. So can somebody suggest me something? How do I ensure that 4 goes to its deserving location? It's just a matter of one swap. Can you tell me which element should I swap 4 with so that 4 goes to its deserving location? It should be H. Got it? It should be H. Guys, don't you think so? Because everything in this part is smaller than equals to 4. So you can now just make this 4 come over here and make this 3 come over here. That way what would happen is that you would have 3, 1, 2, 4. Now see, everything, this 3 anyway was smaller than equals to 4. So it doesn't matter whether it is here, here or here. That is the reason you easily swapped it with this. So 3, 1, 2, which are all smaller than equals to 4, comes to the left, and everything that is there in the right, that by design is strictly greater than 4. I'll give you another example. So see, you understand two most important things over here, that there is an L pointer and there is an H pointer. And do you understand how they are moving? Yes, no, do you understand how L is moving? As long as you are continuously getting the elements which are smaller than equals to 4 in the left, you will move on. Similarly, as long as you will continuously get elements that are strictly greater than 4, you will keep on decrementing your high pointer. Now, the moment you see that L and H have still not overtaken each other, okay, but they have stopped somewhere. So in order to unblock that journey, you would want to swap them. And swapping makes a lot of sense, because everything smaller should come to left and everything greater should go to right. Okay, so you will swap them. And then again the same journey of coming closer will start. The moment they overtake, you would break. And after breaking, as I showed you over here, you would simply swap the first element with the H. Okay, why? Because you have to ensure that it goes at its deserving location. Nothing will go wrong. Still, all the elements that are smaller than equals to 4 will be in left, and all those that are greater than 4 will be there in the right. Let us take an example. So let's say you have 7, 1, 5, 11, 2, 9, 19, 20. Let's say this is the case. Okay. So there'll be a one pointer over here, there'll be another pointer over here. Okay. So can you tell me, so first this pointer will keep on jumping as long as it faces elements that are smaller than equal to 7. So can you tell me at which element this pointer will stop? This pointer keeps on moving as long as you are getting elements that are smaller than equals to 7, right? So you'll move from here to here. Now again here you see that this element is smaller than equals to 7, so you are happy, you move. But when you are here, you will not move, you will stop over here, correct? Same thing over here. Can you tell me where will this pointer stop? So this will keep on moving in the backward direction as long as it is getting greater elements. So 20 is greater, I am happy, I'll come back. 19 is greater, I am happy, I'll come back. Okay, now let's say instead of 9 this was something like 3. Okay. Now would you come back? Would you come back now? No, because this 3 is not greater. Okay, this comes into the category of smaller than equals to. So see, the moment you see that this is a different category, category 1, and this is a category 2, and everything from here to here is category 1, and everything from here to here is a category 2. So the reason you swap is such that the category 1 thing comes over here and category 2 thing comes over here. That is the reason you swap. Okay. So now you will perform swap of this and this. So when you do that, what happens? 3 comes over here and 11 is over here. Okay. Your low was here and high was here. Now again, the same thing will start from the left and from the right. Okay. Will this pointer move? Will this pointer move? Yes or no? Yes, because 3 is smaller. So this will move. Will it move again? Will it move again? Yes, because 2 is smaller. So this L will come over here. Now how about this H? Will this H move? Will this H move? Yes, because 11 is strictly greater. Okay, so this H will come over here. Will this H move now? Will it move now? No, it will not move. So it will basically break. Okay, so now it has broken. So now what would you want to do? Now you can clearly see that everything from here till this H is in category 1, and everything from low till the end is in category 2. Yeah, what will be your last step? Now you would swap H with the first element. Yes. So that way what would happen is this 7 comes over here and this 2 comes over here. So you have 2, you have 1, 5, 3, 7. Okay. So everything in the left is smaller than equals to 7 and everything in the right is strictly greater than 7. And now you would recursively call for this and recursively call for this. So let us think how I can write the code for this. Okay. So let's just take a look here. So when does your process terminate? Whatever you are doing, when does it terminate? Can somebody tell me that? It terminates the moment L becomes greater than H, right? So what I would say that as long as I am seeing that my L is smaller than or equal to H, I will keep on doing something. Okay, I'll keep on doing what I was doing. But before that, I would initialize, let's say the zone was from I to J. Can you tell me what will be the value of L and what will be the value of H? It will be I plus 1. Okay, it is from I to J, right? So it will be I plus 1 and it will be J only. Okay, yeah. Now what will come over here? So you want this pointer to keep on moving as long as you are getting elements which are smaller than equals to pivot. Okay, so for that you would say that while I am getting the elements which are smaller than equals to a of I, which is my pivot element. Okay, till that time I will keep on doing L++. Okay, is it right, or should I have a safety check condition also over here? Can somebody tell me that? Yeah, because what can happen is that this L, so as long as you are seeing that your elements are lesser than equals to this, you are moving ahead. So let's say if you had 1 7 1 5 4 3, so in that case this L would surpass this and come to the end also, right? So you need to have a safety check around that so that you do not hit the end of the array, right? I think we have done this in many other coding examples also. You are getting this or not, right? It can very well happen. This is 7 and this pointer grows when it sees that the elements are smaller than equals to 7. So it would come over here, which is the end of the array, and it would now try to check for this. You do not want to check for that, right? That is not within your zone. Okay, so you would have a condition over here that while your L is smaller than equals to J and this thing is true, then you will do this thing, right? Cool. Similarly, you will have a condition for backward pointer also to move. So you will have while something. Okay, who will write? Just write the proper set of conditions that will come inside this while loop to change the high pointer. It is high, it is not J first thing, and it should not be 0, it should be I, because your high pointer that was initially over here is moving in this direction and this index is I. So you do not want this H to overtake this index I. So you will write something like this, that while your H is greater than equals to I. Did you get this thing? Yes, no? This should be the safety check. While your H is greater than equals to I, and what will be in the AND condition? And as long as you are getting elements that are strictly greater, because equal to is being handled over here. So do not put equal to over here also, that way you will muddle up your code. So here, as long as you see that A of H happens to be strictly greater than A of I, you just keep on doing H minus minus. Now what would happen is that L would have reached somewhere, H would have reached somewhere. So this for loop and this while loop and this while loop, both of these would have got over. So what would you do now? To unblock it, to run again? Yes, you would swap what with what? You would swap A of L with A of H. But would you always swap? Tell me this thing. Would you always swap? No. Yes, because you need to break if L and H have overtaken each other. If L and H have overtaken each other, then you would simply want to not swap so that break can happen based on the condition of outermost for loop. So what would you write? That if L is smaller than H, then you would perform a swap of AL and AH. Okay. So this way, now again, let's say if L and H were apart, they had not overtaken each other, again this logic will run. Okay, in the end, when this entire while loop is over, you would want to perform a last step. Can somebody tell me what would be that last step? Because till now you have not been able to position the pivot element at its location. So what should your last step be? Anyone? You would position pivot at its location, right? So you would swap A of H, and I showed why A of H and not A of L. Okay, because this is the category 1. Okay, and you want category 1 to lie to the left. Okay, so in the last step you would simply swap A of what? A of I with A of H. Okay, what is the time complexity of this code? Yeah, this is order n. Although there are while loops within while loop, but any element is being touched only once, either by left pointer or either by L pointer or by H pointer, right? Okay, cool. So generally people, I have seen some people, they tend to mug up the partition code, but it is very clearly, it is very, important to understand that what is being swapped with what and why these kind of conditions are there. Okay, people generally muddle up with things like this. They'll put lesser than equals to here also, and they'll put equality here also. So that will lead to trouble. No. Your category 1 has to be entirely different from category 2. There should be no intersection between them. If you put equal to at both the places, there will be some intersection and your code will not function as expected. Okay. Another thing to understand clearly over here is that tell me one thing, would it ever happen that h becomes I minus 1? Look at the code and tell me, would it ever happen that h becomes I minus 1? Okay, so your h starts from j and comes back. Let's say your h came at I. If your h came at I, this condition speaks ai greater than ai. Will it be true? No, it will never be true. So h at max in the worst case can become equal to I. Okay, are you getting my point? Yes, no? And can you tell me for which kind of subarray h will terminate at I? I think wise ones should be able to speak that loud. For which kind of array h will terminate at I? If the array is sorted in increasing order, right? Because if the array is, let's say, sorted in increasing order 1, 2, 3, 4, in that case, will this pointer grow? Will L pointer grow? Why will it not grow? Because it will never see an element which is smaller than equals to 1. But what about this h? This h in this loop itself would come and terminate over here. This kind of situation would arise when the first iteration of this and this would have got completed. Yes, no? So in that case, you would swap I with a of I with a of h. Now I and h are same, so one gets swapped with one. And now there is no left subarray, there is just one right subarray that you invoke your call to. Okay, so why I'm speaking that is because of this kind of code that I have written over here. It would never happen that my h goes out of bound. So I have to never check upon the safety of this index. I have to never check upon the safety of this, right? But in the case of L, L, can it happen that L becomes equal to j plus 1? Yes, in the case of L it can happen. Can you give me example of an array for which kind of array L will become j plus 1? If the array is sorted in descending order, very good. So if the array is sorted in descending order 4, 3, 2, 1, in that case your L will be here, your H will be here. Will your H be able to grow? Will H be able to grow back? No, because it will never see an element which is strictly greater than 4 because the array is in descending, right? But what about L? This will see that this thing is smaller than equals to 4. It will be happy and come here. Here also it will be happy and come here. Here also it will be happy and terminate there. And because of this condition, now this loop would have ended. And this loop would never run only. Again you are okay because your H was here and you would swap this with this. So 1 comes here, 4 comes here, and this is your left subarray. Okay, so the way these pointers, the way these conditions have been put, it is very, very important, and you should know answer to whys of those. Otherwise people get runtime error very often while implementing this version of partition. If question asks you to consider something else as the pivot, just swap it with first element and just apply this code. It is a good idea to even remember such kind of code because it comes in handy. It is actually a good idea to remember some codes, like good idea to remember merge procedure, good idea to remember code for merge sort, good idea to remember code for this partition. It helps a lot. Okay. Okay, so this was my partition. Okay. Now, how is the code for my quick sort going to look like? So let's say this is my quick sort. This will take low and high. So this denotes the portion of the array which is supposed to be sorted. So initially low will be 0, high will be n minus 1. And it will have a return type of void. This is not returning anything. Okay. Cool. So tell me, what does it do? What is the first thing that it should do? So in merge, yes, in merge sort, did merge happen in the beginning or did it happen in the end? Did it happen in the beginning or in the end? It happened in the end. So that was a divide and conquer. What is divide and conquer? Where first division happens and then conquer happens. But here partition happens first and then division happens. So is this a divide and conquer? Can I call this thing as a divide and conquer? So listen to me again. In merge sort, You first split your array into two parts. When they are sorted, then you conquer, which is you merge. So in merge sort, what happens first? Divide or conquer? What happens first? Divide. So first you divide and then you conquer the result. So that is divide and conquer. But here is that the case? Simple question. Here is that the case? No, that is not the case. So should this be called as divide and conquer? So this is not, I mean, you might end up having some people say that this is also a classical divide and conquer. But if you try to understand technically, then I would say this is not divide and conquer. Okay, this is something different than that. This looks like that, but in reality, it is not that. Okay, cool. So yeah, so as all of you said, the first thing that would happen would be the partition process. Okay, this partition function, does it need to return something? Does it need to return something? Yes, no? Yes, it needs to return me the index where pivot has been placed, because based on that index only I can tell the range of index for left and range of index for right. Okay, cool. So let's say it tells me that pivot index to be I. Okay, and now what I can do is I can call quick sort for my left part. My left part will vary from where to where? Can you tell me the indices for my left part? What will be the set of indices for my left part? Yeah, it will be L to I minus 1. And then for the right part it will be what? For the right part it will be I plus 1 to H. Okay, so in this code, did I have a check to ensure whether my left part is empty or not, or right part is empty or not? Did I have any kind of check in this code? Yes, no? Did I have? Yes, no? I did not have, right? So how do we ensure that such arrays which are having illegal values of L and H, which are empty, they do not get processed? So I can easily handle that by writing something like this, that if L is smaller than H, then only I am going to do this thing. Okay? Because if L is equal to H, I want to terminate, and if L is greater than H, that points to empty array, right? So I can have this check, and this will take care of literally everything. For empty array, what is the relationship between L and H? L greater than H, right? Yeah, so that is the case. Okay, and you want to terminate for empty arrays, and you also want to terminate for arrays that just have one element in them. So in one element array, L will be equal to H, right? So you are not doing anything for L equals to H and L greater than H. You are only doing something for an array that has a size that is greater than 1. I would recommend you guys to write more code, because if let's say, it's okay if you are slow at understanding these things, but you should ideally not be, if I have to be honest, because if you are actually solving the questions of homeworks and assignment, this coding part should be extremely easy to get. Okay. Okay, tell me one thing. I will leave it as an exercise also for some of you. What do you think? The kind of quicksort that I just wrote, just with the kind of partition, do you consider this to be stable or unstable? Yeah, so with this kind of partition, it will be unstable. I'm not going to explain that how, because I leave that as an homework exercise. I also leave that as a peer group exercise. When you guys meet together, please discuss it. Please discuss, don't just ask that what is the verdict, but ask the process and thought behind that verdict, that why do you feel it is stable and why do you feel it is unstable. But can I make it unstable just by changing my partition process? Guys, how about the first partition process, where I was extracting all the lesser than equals to element and then greater than elements in the other half? So if you do something like this, that can you guys, are you getting what I'm trying to say? Do you remember the first partition process, which was the easiest one, where I was extracting the smaller elements in one array and larger elements in another array and then doing? So can you do something like that to ensure stability? You can do, right? You just have to ensure one thing. Let's see, smaller elements will definitely come in the left, larger elements will definitely come in the right. Now, how about the elements that are equal? Where should the equal elements go? should they go to the bigger array or smaller array? Where should they go? So if let's say you considered this 5 as pivot and you got 1, 4, 5, 11, 2, 9, 17. Okay, so let's say this is your smaller array and this is your bigger array. So you start your journey from here and you terminate till here. Where will you put this 1? For sure here. 4? For sure here. Where will you put this 5? Will you put it in the first array or second array? You will put it in the bigger array. Why? Because if this thing has got repetitions, then those repetitions are definitely having index in the right side of this, and so they should come later. Okay, so this 5 will come here, 11 will come here, 2 will come here, how about 9? 9 is greater, will come here, 17 is greater, come here. So now this 5 will come here, and now you can see that this was first 5 and this was second 5, and this is how I want it to be. So by this one small adjustment you can ensure stability in quicksort.